So we're really excited to have Piper.thunstrom. She's a she's Pythonista, game enthusiast, and web developer. And you might know her from giving conference talks and at conferences and local meetups, and for her open source work. She often speaks on community building, game development, computer science education, and trans identity in tech. She's also the founder of the PPB project. Piper has been involved in the Python community since 2014, and a previous organizer is for the New York City Python users group. You can follow her at piper.thunstrom.dev, and we're really excited to have you give a talk on building games with PursuedPyBear. Piper, welcome. Thank you.
Thank you. All right, so while I do some of the introductory stuff, like I said, this is a tutorial. You can totally follow along if you've got your IDE ready. I have, in fact, put this up on, all of my notes are on GitHub. No guarantees that the everything is great, but there is a link here. You are going to want to grab one of the resources archives. For some of what we're doing, you need a font file, and I didn't have that instruction for you to all find one you liked. So this is one that's going to work. It also has a requirements.txt that you should use for setting up your virtual environment for whatever project environment you want. If you would rather just type it out, these are the two requirements, and you should put them in this order. So let me talk about what PPB is as we get started. So PPB is an education-focused game engine. And a lot of people ask, what does that mean? And it's basically, I started PPB mostly for my own benefit, like many open source projects. I was using Pygame at the time and didn't like a lot of the boilerplate I would have to write for every project. So I started writing a lot of that into a thing that would become a game engine. And as I started showing off that tool to some of my friends, I am friends with a lot of educators, they went, can you like make us a thing that works in the classroom better? And that's really the start of what PPB is today. In a lot of ways, what that means is anytime that there is an engineering choice that there's like 3 valid engineering solutions, the tiebreaker tends to be me going and asking a bunch of teachers who teach CS or game development and go, hey, which of these look better for a classroom environment? So if you have questions about like why we may have made a specific decision, you're welcome to ask them. But a lot of times that's the answer is I had a teacher ask for that exact feature. So if everyone has an environment set up, does anyone still need some time? Is I think the better question. Sounds like no. Okay, so I've already got mine set up. I have already installed these 2 libraries. Here's my main file. You can call this whatever. Everything we're going to do today, it's a single file game. Not my favorite way to do things, but it's very easy and fast. And so the very first step of this process is, this is a thing I teach everyone to do when they start making games, is the very first thing you want to be able to do is open a window. And so in PPB, that is very simple. We just import PPB and PPB.run. So if you run, once you've written this, if you run the file, you're going to have an open window. That's as much work as we wanted to make it do. This has a lot of things going on under the hood. The one that for people who are used to Pygame and the basic setup and teardown, the close button works as expected. So that's one of the things we wanted as part of this, is that you don't have to write event handlers for shutting your game down. So this is the first thing. The game that we're going to be making today is a breakout clone, a brick breaking game. And so those games tend to be vertical instead of horizontal. So what we're going to first do is update the resolution to 600 by 800. The default resolution in PPB is 800 by 600. That's another one of those. I talked to a bunch of teachers. That is the very common default in education resources because it works on just about every machine on the planet. This keyword argument is actually not part of the run function specifically. The resolution keyword argument is actually passed down to a part of the engine called the renderer. So arbitrary keyword arguments here, as you can see, my ID is telling us what this will allow. The engine options are all passed down to the engine and then eventually to all of the subsystems. And so resolution actually comes from our renderer. And now if we run this one, we now have a vertical window. So that's all we've done now is turn the whole thing on its side. If you'd like to give your game a title, there is a title. And one last time, as you see, the name of the window is now Brickbreaker instead of PursuedPyBear. If you don't provide it, we're just going to put the engine name up there because that's what we do. All right. So the next step of building games that I tend to suggest to people is there is a concept, a dev recently coined the term for it, of the Seashell Method or the shell method. And it's named after the idea of a Nautilus shell that starts very small, and as it builds up, it spirals around and gets bigger and bigger. So we're going to make something very small that is functional. It won't look like a game, but it lets you do some stuff. And then we're going to add to each piece as we come back to it. So when we are talking about parts of a game in PBB, we use a concept called scenes. Scenes exist in a lot of game engines. The reason we've picked that word is primarily because it exists in other things. And so PBB has a scene base class. So if we have a title screen, we call it. So this is defining a new scene. So scenes are one of the core object types in Python. The underlying model is referred to as game objects, and they all have a shared init. They're all containers. And once they're in the object tree, can respond to events. Those are the three important things of all game objects. We're going to make 3 of these because we want a title screen, we want a game screen, and we're going to put a game over screen, which I'm just going to call end screen. The names of these are arbitrary. You can name them something different if you prefer. But if you want to follow along, try to keep to the naming I've got, because that's what I'll be writing on screen. So if we do this, PBB itself doesn't know that these exist right now. So we actually have to tell PBB via the starting scene attribute what scene you want us to run. There we go. So this is going to do the title screen. Right now, because it's just the base scene, it's going to be what we've already seen. So what we're actually going to do is add a background color. And we're going to just make the background color of the title screen black. So if we run this now, we've got a black screen instead of a blue screen. Ooh. I know this isn't much, but this is going to be important in a bit. Quick talk about colors. So colors, PBB uses them in either 2 ways. Either an object is going to request the red, green, and blue channels specifically, or it's going to be a three element tuple like this that represent red, green, and blue. The values that are valid for that are 0 to 255. So some of you will recognize that's an 8-bit integer. All colors in PBB are 8-bit integers. So if you wanted to make your background white, you would just make this 255, 255, 255. And we'll be using a bunch of different colors. Feel free to change these values at any time during this tutorial. You make it your own thing. Whatever you think looks good is totally going to work and not change anything else in the system. So the next step is we want to be able to go from the title screen to the game screen, and then from the game screen to the end screen, and then back to the title screen. So to do that, let's first define some background colors, make each one of these a slightly different color. Hold on, I need to find my note on what I actually liked for these. All right, so this is a very dark green. And this one I am making a dark red. Again, as long as these are visually different for you, it doesn't matter. This is just so that we know that what we're programming is correct. There we go. So this, again, if we run it, nothing's going to happen. We still have only the black screen because we've not told PBB how to move between these. So our first thing is we have to write our first event handler. And so the first one we're going to write is the key released handler. And this is the shape of all event handlers in PPB. And I'm going to talk through this before we go on. Key released here is actually a PPB events.keyReleased. I'm going to use some type hinting because it makes things easier to see. So this is the key released event. This is the actual object that represents the event. And so we take the name of the event and make it snake case and add on to the front. So on key released responds to the key released event type. All handlers look like this. So if you go look in the PPB events list, you can always figure out what you need to make because they all look like this. The next step for this, we're actually going to have this, any key you press, when you let go of the key, it's going to move from the title screen to the game screen. So we're not checking any information on the event, but we are going to use that signal function. The signal function takes an event type as its only, or an event instance as its only positional argument. So in this case, we actually need to use the start scene and then tell it to use the game screen. All right, so this is a very basic idea here. The way scenes are held in the engine is actually in a stack. So whatever your first scene in is going to be at the bottom of the stack. And when we say start scene, the engine is actually going to instantiate that new scene and put it on top of the stack. During the event loop, the only thing that's actually running is the top of the stack. So we peak at the top. That's the one that gets all the events. If it ever stops running, the one under it will start up again. So that's basic event structure for us. And now if we do this and we hit this, press any keyboard key and it changes colors. So that's step one. We're going to do basically the same thing in our game scene. Def on key released. So exact same signature as before. But when this one gets it, we're actually going to use a different one of these events. We're going to replace the scene with the end screen. So basic stack control for those who don't know. A stack's primary operations, you have a push and a pop. Push is put a new thing on it. Pop is pull the top thing off of it. Replace is a pop and then a push. So when we call replace scene, the engine's going to take off the game scene and throw it away. And then whatever scene we gave it, it's going to put on top of it. So this will replace the game scene with the end screen. And then the last one we're going to do, def on key released events dot released signal. And yes, this becomes a muscle memory thing eventually. PPB events dot stop scene. So stop scene is different from the other one, the other versions of this event, in that stop scene doesn't need a next event. In this case, this is the pop for that stack. So we're just saying when we press the button on the end screen, we just want to like remove the end scene and whatever's left is going to run. If for any reason you call stop scene and it's the last scene in the scene stack, the engine will actually quit gracefully after that point. So it actually knows to check, hey, do I have any scenes? Okay, I can actually shut down now. And so now if we run this file, we've got our black screen, which is our title screen. I press a key, we're in the game. I press a key, we're in the red. So now we have like all three. If I hit it again, I'm back to the title screen. So now you can see our basic program flow. We have our menu, our title screen. We're going to go from that into the game. And then when the game ends, which right now is just we hit a button and it ends, and then we can jump to, that'll show us an end screen, which when we press a key there, takes us back to the title so we can play again. So real basic program flow. This is done. Are there any questions at this point? Okay.
There's no questions in chat, Piper. Anyone have any questions? You can come off mute if you want.
All right, so that's that. So our next step after this is now we're going to actually put something on the title screen so that it's not just an empty blob. If you downloaded the resources pack, there's a font there for you. So we'll use that for this game. If you have some TTF or OTF fonts lying around, any one of them should work. You do want one that actually has number glyphs. There was a bug in an earlier version of this talk. So, so this is where I get to talk about, we're going to make a constant that is a font file. And so that is a ppb.font. A font is one of the very many things we refer to as assets in PPB. An asset is basically any file that is not code that you might want to use. So image files, font files, text rendering, things like that. All of those are represented by what we call assets. The asset system, when it needs to access the file system, basically knows what the Python path is and can find things anywhere in that path. We do cheat a little. We put the current working directory on the Python path for you. So files that are right next to your main file, you can just put the file name in. Otherwise, if you put them in a resources folder, you can go to resources / file name, and PBB will figure out where they are. And so in the case of a font file, we actually need our Rubin expanded. I'm just gonna cheat here. If you're using PyCharm, there's this wonderful copy path or reference, and you can just get the file name out of that menu. And then you have to give this a size. So I have to talk a little bit about font sizes. So the underlying font system uses code points or font points, which are a fairly esoteric measurement system that was used in old school printing presses. When you're using this in game, we actually care more about game size. So in general, bigger is better here, but the bigger it is, the more hardware intensive it is to render. So I like using 72. 72 is a nice, like, it tends to render at most of the sizes you're going to use at the resolution of PPB without too much issue. You can make this bigger, and when it rescales down or up, the artifacting is less bad. So that's the only thing you need to worry about there. So the next step, we need to define an init on our title screen. All game objects share this init. We cheat a little in PPB so that instead of having to worry about defining a custom init for every object, because game development tends to be fluid, all of the keyword arguments are going to get set as attributes on the object. So if you just take a PPB sprite and pass a bunch of keyword arguments, you're going to have an object with all of those keywords as attributes. So we're doing this magically. The reason we did background color at this level, like this is so that you don't have to rewrite the init every time. You can just define them at the class level, and they're treated basically as defaults. Once you start changing them on an object, it won't be using the class defined one, it'll use the instance one. But that's what we do for you, so that when you're writing inits, the only thing you really have to do is actually start working with the object. And so in this case, remember I mentioned that all PPB objects, or all PPB game objects, are containers. So they all have an add function. It takes another game object. In this case, it's going to be a sprite. So pbb.sprite. And it's image attribute. So sprites, the renderer only looks for sprites with image attributes that are the direct children of scenes. So the image is actually what gets drawn on screen. Everything else, all the other information, size is the other one that is going to be important. It tells you, it'll resize the image to fit the space that you want it to. And so our image is actually going to be a pbb.text. So this is another resource. This one is actually a font rendered. So when we call it Brickbreaker, and again, you can call this whatever you like. And then it needs a font as a keyword, which we have our font constant. And then we need a color. And this is just a general preference, but pure white and pure black are eh. And so putting a slightly less bright white on the black background is going to be a little easier on your eyes. So we're using 220, 220, 220 for the color. So yeah, this is a text object. So it's going to render Brickbreaker in this font with this color, and then resize it for the size of the object. And so if we run this now, you'll see I've got the text. It's a little small, kind of hard to read. And so the way to change that is not actually to change the font size, but the size of the object. And so our PPB sprites are always squares, so we can use a size attribute instead of width and height. And let's just make it 2. As you can tell, that means that this text is actually rendering outside the bounding box. I am working on something to magically figure out what the bounding box on this text should be, but not in the engine yet. But there we've got a size 2. We've got the title, middle of the screen. We've got a working title screen. So any questions on what I just covered? Sounds like no. Oh, okay.
Yeah, can the size be anything like 1.5 or something? No, right? It's only in the sizes of like.
Oh, yeah. PBB sprites can be, it is a continuous. It's not integers.
Oh, okay.
So I will talk more about the way size interacts with the underlying game grid in a little bit. For now, it was just, this is how you resize text, is if you do this. And so this is actually ends up being, for almost all fonts, when you're talking size, this is actually how many game units tall you want the text to appear. And I will go into that into detail in just a moment, because this is a working title screen. You can add more text to this. There's a position attribute. We're going to be using it a lot in just a few moments. But yeah, you can spruce this up any way you want. One thing I am not explaining, I don't show off in this tutorial, but there is a pbb.image that works very similar to font, except all you have to give it is a file name. So if you have a PNG, you can drop it in here and load a PNG the same way, using the PPB image object. So that is all that detail. So we're going to move on. That's the title screen. That all works. So now it's to get onto the game itself. So the first thing we actually want to do for our game is we're going to make the actual ball. And we're going to call it ball because, I mean, that's what it represents in the game. So this, we need a PPB sprite again. And now we get to talk about all of these things. So the 2 things that I want us to do here, let's just pass for now. And I'll show you one of the niceties that PPB does for you. So we jump down to our game screen. We need a new init. Thank you. All right. So same init as before. This doesn't need to do anything else. Now we do self.add, and we can just give it the ball class. I'm going to do this so that if we want to manipulate its runtime environment, we can do that. And so we run this. All right, so here's our title screen. We press a button. Now I have a square on screen. If you're following along, your square is probably a different color. And the reason that is that if you do not provide an image attribute for a sprite, we actually will render a square for you. And the color we pick is actually based on the hash of the class name. And hashes in modern Python are different from system to system. So even though we're just hashing the name, there is a random component that is system specific. And so your color is going to be different, but if you run this game multiple times, you're not going to get a different color. You will always get the same color on your system for the same class name. So that's nice, but not really what we need. So here we are going to do another image because I don't have a PNG for this. I'm just going to use what we've got built in. We have a circle class. This is another one of those asset types. This one is just, it renders a circle in the background so that we can render it. And so same thing, I'm going to use that same 220 across the board. And now it's a white circle. I hit run. We go. And now I have a slightly gray ball in the middle of our scene. Yes, it's squished. For folks who are used to open source and want to come like play with our renderer to make them not squished anymore, I'm happy to walk you through that at another time. All right, so now we've got an image. It's in the middle of the screen. The next thing we want to do is to make this move, because that is like the heart and soul of a breakout game, is that bouncing ball. We're going to give it a velocity, and we're going to use our directions module. Use up and multiply this by 10, and then position equals is a vector, and we want it to be, we're actually going to move it down the screen. So this is where we're going to talk about game units and what this all means. Both of these attributes are PBB vectors. The directions module is a series of what we call unit vectors, which are vectors with a length of 1. The important thing, I am absolutely going to be glossing over a lot of linear algebra here. So anyone who knows linear algebra, I know it's not exactly true what I'm about to say, but it's useful. So unit vectors, basically a vector is represents a direction in space. So our position here is if you're starting on a point and you go south 13 miles, that's essentially what this vector is telling us, is go south 13 units. The reason I keep using unit is because PBB units are arbitrary. The ball is actually 1 unit wide. So if you want to get an idea of the pixel to unit ratio, which is a thing that we calculate for you, you don't have to think about this much. 1 unit is the default size of a sprite. In the case of up, a unit vector is, again, a unit that is 1 unit long, or is a vector that is 1 unit long. You calculate this, you use the Pythagorean theorem, except for these vectors that are like orthogonal, because it's just whatever the non-zero component is for length there. So I take a unit vector of up and I multiply it by 10. So this is a 10 unit long arrow pointing up is what you should be imagining when I do this. All right, so that's game units, the underlying grid, and vectors, because these are all important things. And I'm using the named vectors in PBB, except where we need specific things. And so mostly just know that you can do some cool math on vectors that will do element-wise operations. We do all this for you. You don't have to think about it. So to do the actual movement, though, we do an update event. And same as before, this is PBB events.update and a signal function, which we don't need on this one. And so what we're going to do, self.position plus equals self.velocity times events.time delta. All right. So those with a physics background should recognize this as a simple integration equation. This is basically, so let me explain the points here. So the update event is as far as your game is concerned, the heartbeat of your game. By default, PPB runs simulations at about 60 frames a second. And so the time delta is how much time passed since the last update event. We use what is called fixed step simulation. So the time delta is always going to be the same, but that is a default behavior. It is something that can be changed. So we just make sure that the update event that gets sent always has a time delta so that you can do variable rate if that's what you want to do. But so we multiply the velocity. So the velocity is units per second. We multiply that by the time delta to get the portion for the last frame. And then we add that to the current position. And that is our new position for the ball. And that is a lot of words to say the ball goes up. But you should, so there we go. We've got a moving ball. That's step one of making our game. It's not bouncing off of anything yet. So that's our next step. So the next step is we're going to do another class. That's our wall, pbb.sprite. Oh, actually, this needs to be a rectangle sprite because the walls are long and thin or wide and thin. And so what we're going to do here is, first thing is we need a def, we need another initializing function, just like on the existing things. We do super init works. All right. And then we have to do it here because, let me just explain as I go. All right, pbb.rectangle. So rectangle sprites are actually one of our default sprite types. The sprite that we used up here is actually a subclass of this one. Or I don't know if it's a subclass, but it shares a lot of behaviors. The rectangle is not fixed size. So it doesn't have a size attribute. It has a width and a height that are separate. And the reason we have to do this in the init is because we will not know the aspect ratio of the object until it is instantiated. So let's do the same thing. Red, green, blue, the same. And then aspect ratio is basically the width to height ratio. And we can actually cheat this as well just by doing self.width, self.height. We don't have to define these here because width and height are defined on one of the mixins. But this will make sure that the image fits the space that the wall takes up. And so let's go in. I want to do one more thing before we add this to it, because we're going to need one more value when we start doing wall collisions. And so we're going to add a normal to the wall. And a normal vector is a length 1 vector. So those the directions are already normalized vectors. The normal in the case of reflection is it's a vector pointing perpendicularly away from the surface. So I'm going to put a default here of directions.down. And then I will, as we implement this, I will walk you through this. So this is what we need for our wall. Is everyone good here? Is there anyone who's fallen behind and I need to show them part of the code again? Okay, so I'm going to scroll down. We're going to go into our game. We added a ball. So now we're going to do self.add wall. This is another one. I'm going to have to go look at my implementation to make sure I get certain things correct. All right. Actually, okay, so we're going to step back a second. As we implement this wall, the width and the height are currently an unknown. You know the pixel dimensions of the space, but you don't know the unit dimensions. So we're going to go up into our on-key released, and we're going to print. Basically, what we need to get is the camera that every scene is given by the renderer. Because this is actually in a scene that I'm working in with the title screen, we can do self.camera to get that, or not camera class, self.mainCamera. But you might not be working there. And so the way to get the camera is event.scene main camera, because every scene is going to have a main camera after it's been initialized and started. And every event gets a scene added to it, which is the currently running scene. So we grab this, and then we're going to just print W is camera.width, height, camera.height, and then we hit play. And when I hit a key, you see in my terminal, we've got the width and the height just printed out for us. So that's the width and height of the game field in game units, not in pixels. You now have enough numbers that you can calculate what the engine's doing under the hood. So the wall for the top is going to be width equals 25, or actually, you want to make it a little bigger. You want it to overlap outside the play space a bit, but so we'll do 26, and then our position is another PPB vector. So it has to go up. So the X component is 0 because it's not moving left or right. And then it goes positive direction. And I need to double check this one. 16.5 units. So like I said before, they're continuous. You can put any float. The precision is, I think, minus e to the 5 is the actual guaranteed accuracy. It's going to depend on your system and what the float chip is doing.
Pretty sure it's higher than it's IEEE double, which means it's like -15, I think.
Oh, okay. Thank you, Jamie. Like, it's been a while since I've checked.
No, it's higher. If you all want to hear about our adventures with floating point, ask us after the talk.
All right. So this is our first wall. This is going to be at the top of the screen. And I'm going to rerun the game real quick just to show you. We now have a line at the top. So we're going to basically do the same thing with the other 4 sides. So let's do the wall at the bottom, which is going to be width equals 26. And position is going to be the same vector, but inverted. So 0, -16.5. So that'll put it on the bottom of the screen. Add wall height equals 34. So these are going to be the side walls. The position, just like we only changed the Y vector for going up and down, we only changed the X here. And we need 12 units to go to the right. Oh, and I actually skipped a thing. Remember I mentioned the normals? So the wall on the bottom actually needs to be directions dot. It's pointing up. This is the right-hand one. So this normal is PPB directions dot left, because it's going to, if it's on the, okay, my left. So basically, if it's on this side, it needs to go that way. And if it's on this side, it goes that way. Does that make sense? All right, and then last one, self.add wall height equals 34, position equals PPB vector -12, 0, and the normal is the opposite side. Right. Okay, so we're going to stop for a second. Questions while I demo this. So once we get into the game, we have white lines all the way around the outside of our game space. But as you notice, the ball still flies off screen. PPB does not have a physics engine built in. You have to either write it yourself or use one that's out there. I do not believe anyone has written a full physics engine that integrates with PPB yet. One day. So what we're actually going to do is go back up to our ball, and we need to get all of the walls. So this is where we're taking advantage of the fact that we know that the scene exists on the event, and then we're going to get, this is not going to work the way like key access works for a dictionary. There are two ways to search for objects in PPB. It's either by kind, which is the type of the object, or by tag, which is when you add to a scene. Let me see if I, so let's change it for this one. I can add a tags keyword argument to this add, and I'm gonna just tag it deadly. We're not gonna use this for a while, but keep it in mind. So we come up to the ball. So we need to just get kind equals wall, and then for wall in walls, let's pass, because so basically the first thing we want to do is if self, we haven't written this function yet, so it's going to complain at me, but we want to see if we collide with a wall, and then we're going to do something. Let's go down, def collides self other. So other is always some kind of PPB sprite. It's either going to be a rectangle sprite or it's going to be a standard sprite. And the way we're going to write the collision. So this is a very simple collision test. And by very simple, there are much more complex collision styles. This is one of the most simple versions that are available to you. So what you do is you get the combined width of the objects. So self.width plus other.width. You get the combined height equals self.height plus other.height. Then we want to get the max vertical distance, which is max self.top. So we basically want whichever object is higher on screen, we want its top. So we actually just get, we use the max function here, and then we subtract the minimum of the bottoms. So what this is going to give you is the highest point between both objects and the lowest point between both objects. And then we're going to do the same thing, max horizontal distance. And it's the same function, but max is right. And so this is just, if you think about the grid that I mentioned before, negative. So if you think about like a Cartesian coordinate, like you would do in grade school, going to the right, the numbers go up, going to the left, the numbers go down. And so our right is going to be our maximum value, and then self.left, other.left, and then we return combined height is less than, or yes, is less than the max vertical distance, and the combined width is less than the max horizontal distance. And this is a lot. I will admit, this is fairly complicated when you first start playing with it. Basically, what it's saying that is if you take the furthest right point and the furthest left point, and that distance is less than the combined width of both objects, then they're close enough to touch. And then if it's also the same thing, highest point to lowest point is less than their combined distance, they're close enough to touch. If both are true, that's a collision. That means the two boxes overlap. This is fun stuff to actually play with in your free time. Collision algorithms have some like really, really interesting algorithms out there. So now we know if we've collided with a wall. And so what we want to do at that point is self.velocity equals. So our vector class has a reflect method. You give it a surface normal and it will reflect across that surface normal. So that's why we actually needed the walls to have a normal. And there we go. And so what we should see when I run this file is the ball is going to go up to the top, hit the top wall, bounce off, and come back to the bottom. So we do this. There it goes. Oh, it did not work. Did I do this wrong? Oh, yep, I inverted this. Sorry. So yes, double check your code here. Combined height should be great if combined height is greater than max vertical distance and combined width is greater than max horizontal distance. So now we've got it bouncing off of the top and the bottom. And then if you want to make this more interesting to look at, there is an up and right, which is the 45-degree angle. And now it's going to bounce off all the walls. All right, so there, we have walls working. Any questions for where we're at? Okay, so we're moving on. Next step, let's add the paddle to the game. This is the next complicated bit. They actually, things get easier after you get these two set up correctly. Paddle. This is going to be a rectangle sprite. Not rectangle sprite. Those are different things, and it will do bad stuff. We are going to need an init, but it is literally this same init. So if we just do this, and then we can pick a color here. I worked with a light blue, which looks like 175, 175, and 255. So you can, again, put any color you want here. Make it different than the ball is totally valuable. The next thing we need is we're going to set the width to 3 because we want it to be 3 units wide. This is another thing. Changing the width is going to actually change how hard or easy the game is. Make the paddle smaller and it's harder to block the ball. Make it bigger and it's easier. So now we've done this. Let's come down here. So this, sorry, down here is back in the game screen. Inside the init, after all of our walls, we do a self.add paddle. Just instantiate it. This isn't going to need anything special because there's only one of them, and we can put most of that on the object, on the class itself to make it work. So if I hit this, enter, okay, now we have it. It's at a weird position, so we will move the position. Same thing as before. We want to start it in the center of the screen. It defaults there, so 0 for the X component, and then -14. You need it somewhere above the bottom, so you can play with this a little bit, but as close to the bottom of the screen as you can get is usually good. And so this, we now have that. Oh, whoops. Sorry, I said we could copy this. I was slightly wrong. So what we're actually going to do is splat the color here. So if we just do this self.color, this is going to unpack whatever color we defined into those 3 arguments, and then the aspect ratio is the same trick as before. So now we hit this, it should be a blue paddle. Oh, there we go, blue paddle. All right, so now we're on to controls. And I'm going to have us do mouse controls, which are a little complicated, but it won't be too bad. Keyboard controls, I will give a quick primer on, but will not have time to show you all of that. So the first thing we need is a target position, and we're going to instantiate it to none, or initialize it to none. So the target position, then we're going to use another new event on mouse motion. So this is PP. This is another built-in event, mouse motion, and then the signal function. So the mouse motion event, most libraries that let you interact with the mouse position is actually in pixels based on the top left corner of your window. PBB does all of the transform for you in this event, so that the actual position of the event is the in-game space position of the mouse, not screen space. So what we can do is self.target position is going to be a vector, and we're going to do something neat here. The x position is going to be the event.position.x, but then the y position is going to be the self.position.y. So what this is actually doing is it's taking the target position is going to be on the same line as the paddle is already on, but the x component is going to be where the mouse is on screen. So that's what we're doing there. And then same as before, we're going to do all of our movement in def on update. So this all looks like our previous one, but our code is a little more complex this time. What we need to do is if self.target position is none, return, because we don't want to do anything if that's not been set yet. So if the player hasn't moved the mouse and so the system doesn't know where the mouse position is, we don't want to do anything. After that point, what we're going to do is get position delta. So delta just means the difference between two things. And so we want to go to the target position from current position. And then remember, we want to do this in little steps. So we would need to do position delta time, or not, hold on, movement delta equals position delta times event.time delta. And then we're actually going to need to define a speed. This is another thing that will define difficulty. So I'm going to put it up here next to width. So if folks want to play with their games later and change how all this works. And we're just going to make it speed 10. And so times self.speed. The next thing we want to do, because this is going to prevent a bug that is, it creates a bouncing effect. So as the paddle tries to move towards the mouse, it might move past it, at which point it then tries to move back towards the mouse from the other direction, and it'll bounce back and forth like that. So to make sure that that doesn't happen, we do greater than position delta. We do movement delta equals position delta. Oh, I actually just created another bug. So because this has to normalize. So if you try to normalize a zero vector, it explodes. And so the way we can make sure that we don't do that is if position delta is 0, we don't actually want to move. So we can just do this. So we move all of that code under if position delta, then we normalize it. And then self.position plus equals movement delta. So you'll note we didn't actually need to do anything on this part of it because we did all of our math up here. All right. So if all of this is working, nope. Oh, yeah. Dot length. Right. So we want to make sure that if the movement delta is longer than the actual whole amount we want to move, we just want to move the remainder of the amount. And so we have to do dot length is greater than dot length. Any questions on this? I know I had to like rewire my positioning on it. So we should be able to do this. And now the paddle follows the mouse. But still goes through it. So it's going to be the same thing as before. We come up to the ball, and in the on update, we get to do a cheat. So the paddle is going to be event.scene.get kind equals paddle. So get always returns, technically it's a set, but it's an iterable is what you need to know about it. So this is going to give us an iterable of one object. So you could loop over this, but because we always know, like if the paddle ever doesn't exist, we're in a bad state and we want an error anyway. So we're going to do just called next, and that will just grab us the one object in our iterable. And then if self.collides paddle, self.velocity equals self.velocity.reflect. And this is going to just be dot directions dot up. So this is kind of a cheat, but what you will find in game development is that we cheat a lot. And so we're just going to treat the paddle as if it is a flat wall that is facing up, and you get mostly what you're expecting out of it. The actual original breakout, the paddle was an ellipse, and I will leave that as an exercise to the reader on how to implement that code correctly. So just to demo this, now we should, once this ball comes back down, I'm going to speed it up for our demos in a second. So there, now it bounces off the paddle. So that's the next step. It goes through the walls. I've kind of shown you some of what you can do for that. Sorry, give me 1 second. Yeah, all right, so we have the ball, we have the paddle, we're bouncing off the paddle. So the very next step is going to be the bricks. And we're going to cheat a lot on the bricks because getting it right is hard and takes a lot of time. So wherever you, thank you, PyCharm, didn't need that. Class brick. And we're going to make this a rectangle sprite. We are making them width 2. And then, excuse me while I check my reference. So we want the width to be 2. This is just a visual thing. And now we're going to do something a little magical. So we're going to do a hits value. So we want this brick to break in 3 hits, for example, is what this sample is going to do. And then we make a colors field. And each one of these is a PvP rectangle sprite, or not, PvP rectangle. And we can just do 255, 0, 0. And then our aspect ratio is 2:1. And we're doing 3 of these. So put them in. Make that 0, 255. So the important thing that you need, if you decide to extend this, is your maximum hits is basically the length of colors. So as long as you have all of this, this code's all going to continue working for you. We're then going to do image equals colors hits -1. So this is setting, when we instantiate a brick, it's going to have 3 hits. And so it's going to put our blue color on the brick for us. The next thing we want to do is do this is another pre-built event for us. There is a pre-render event. This is when we encourage you to do anything presentational. If you're changing the color of things, if you're hand rolling an animation, so you want to change frames, if you're moving UI around, all of this should happen during the pre-render, because the only time it fires is before the renderer actually tries to render a frame. By default, as I said, update 60 times a second, render 30 times a second. That's mostly a like 30. Most systems are able to hit 30. You can manipulate both of these numbers via keyword arguments to the run function. So we're going to do our events.pre-render. Let's see. Signal. And then this, we basically do the same thing. Self.image equals self.colors, self.hits -1. And then just I'm going to rush through this because it's some basic stuff. So from itertools, import product. And then down in our game, we're going to do a for xy in product range. Say, check my reference again. Here we go. -9, 13, 3. And then range 4, 15, 2. All right. So those values are going to work for your game. I'm just like letting you know that this is going to make a working field. You can play with the values that are in the range, or you can write maps that do this. There's a bunch of ways you can handle this, but so we're going to add a brick. Position equals pbb.vector xy. And then we run this. Oh. It was not doing that before. Did I get this wrong? Oh, this is 12, not 13. There we go. So this, if we run it, there you've got your field of bricks. We're going through them. We're going to fix that in a moment. We've got like 2 more things to do, and then this is a functioning game. And then there's more I could show you, but I notice it is already late. So let me go through this. So we're going to go same basic thing. The ball is where we're going to do all our collisions. And so we get bricks equals same as before, event.scene.get kind equals brick for brick in bricks. If self.collides brick. So what we're going to do is we're going to get the normal from the center of the brick to the position of the ball. And the reason we're doing this is because it's easier math than trying to figure out exactly the right normal for where the ball hits the thing. It does make the bricks essentially round under the hood, but it kind of works in practice. So we will do vec equals self.position. So 2 from brick.position. And then if vec, no, vec's always going to be non-zero, so it's fine. So what we're going to do is self.velocity equals self.velocity.reflect vec.normalize. This is a cheat. This is not actually the way the physics are supposed to be done, but it's 2 lines of code. So we do this. If we hit play, okay, so it's now bouncing off of it, but the bricks aren't doing anything. So what we're actually going to do now is define our own system event. So if we go up here, from data classes, import data class. We suggest using data classes or something like adders just because it makes it very easy to define these because they won't have any methods on them. And so we do at data class brick struct. And the only thing we need to actually put here is a scene, which is a ppp.scene. And then we'll initialize it to none because we don't need any information here. You could put the brick that was struck here, but we have a more performant way to handle this. So what we'll do is signal our brick struck event. And then there is a second optional argument called targets. And in that list, we add the brick. And so what this is going to do is when it detects a collision, it's going to tell the brick that it hit, hey, you've been hit. Well, the engine will do it for us. And so now we come down into the brick. And remember what I said about how we define these? Our own event will work the same way. So on brick struct, self event signal. And because we use the target, we can actually make this, instead of going, hey, am I the brick that was actually struck? We can just go hits minus equal 1, or self.hits minus equals 1. And then we do if self.hits is less than or equal to 0, event.scene.remove self. And that is all the code we need. And now you'll see as we hit bricks, they're going to turn colors, basically as their hits go down. And then when they're at 0, they disappear from the field. So this is a fully functioning game. You can actually currently end this by hitting this thing. We can do one last thing for the game end. We'll do deadly wall equals scene.get tag equals deadly. And we'll use that next trick again. And then if self.collides deadly wall. Now this means we're checking collision against the same wall twice. There's other ways we could have done this, is basically what I'm saying. There's almost always another way to do things in game dev, but we're going to do a signal ppp.events.replace scene end screen. And then we can come down to the game screen and actually remove this handler because we don't need it anymore. And game over. And so the end screen is going to be very similar to the title screen, so you all can figure out how to do that part. Are there any questions at this point? I had a whole adding a high score or a scoring system to this, but that would take us another 20 minutes. So,
Hey, Piper, can you go back up in your code to the last part you were working on?
yep.
I fell behind right at the end.
I'm so sorry. I did speed up a little. So this is in, try to remember. So we defined a data class. Did you get that part?
Yeah, I did.
Okay. So brick and bricks, signal brick struck. And then the deadly wall is this one. I'm happy to scroll us back to any of these pieces so that folks can get their version going. But yeah, so that is a functioning game in PPB. The only thing I wasn't able to teach you about is a concept called systems. Systems are the way features get added to the engine, and there is an entire API that you can use to add your own features. the sad part is, besides like writing the system is the long part, the actual like tying it into everything is just like everything here. And the code for that, if you're interested, the repository for this tutorial has all of my notes and an example, like a working example. So there are chapter 4.1, a scoring system, is everything you need to add your scoring system if you want to do that. It also includes like displaying the score, which is an important piece of the puzzle.
Thanks, Piper. Anyone have any other questions for Piper? All right. So
Well then,
thanks so much, Piper. I mean, we went from like nothing to a working game, so it was a whirlwind, but a lot of fun. So thank you so much.
Yeah, I am sorry that went so long. If you want to know more about PPB, yes, thank you, YubiKey. You can learn more about PPB at ppb.dev. That has a link to our Discord, the documentation, the GitHub, also a link to the PyPI entry if that's what you're interested in. Also the Twitter if you want to follow along with our announcements. We have a channel in the Discord if you decide you want to expand your knowledge. We have a Making Games channel, which is, we are happy to answer like that kind of question. If you have, I found a bug, there is a, it didn't work for, I'm not sure if this is a bug or I'm just doing it wrong. And we have the development channel where we will talk about bugs. And we are very open for contributors. So we will help walk you through code review and the PR process if you're new to open source development. Jamie and myself both do a lot of that. And we are overdue on our next release. So one of these days I will actually sit down and get all that work done and get that out the door.
Awesome. Thanks again, Piper. That was a lot of fun. So yeah, really great presentation. Thank you.
Thank you.